welcome guys, welcome to my channel. So before I start, please subscribe to my channel. So my math channel is called Math Geeks, and there is a various video, okay, not like video, don't care. Mathematics, right? So also complexity theory, differential geometry, a lot of machine learning, differential equation, electron dynamics, also some physics, and yeah, basically math, physics. Yeah, most of it, and also GRE math and physics solution, and also some interesting mathematics and physics. Yeah. Okay, so this video, let's talk about advanced calculus, and this video is called Heine Borel Theorem. Okay, so in order to prove this Heine Borel theorem, you need to check out my previous video called boson on wire truss. So boson wire truss is, let's quickly review. So boson wire truss is somebody give you a sequence in the Rn dimension. Then if it's bounded, then always a convergent subsequence. Okay, so we might use this fact, and we may not. So, but this is really important that really connected to this Heine Borel. Okay, so let's prove the Heine Borel. So, also I will leave another video. Basically, I prove these first things is that if A is compact, then A is closed and bound. This is really trivial in in Rn dimension. Okay. Basically, if you have also it's also works for any metric space. But Heine Borel is really important that it only works for the space like Rn, which you need some completeness property. So if A is closed and bounded, A is compact. Okay. Okay, so in order to prove this, let's prove the lemma. So this lemma is very easy. So the assumption is that if A is compact, if A is subset of compact space K, and such that A is closed, then A is compact. So basically, the closed subset of compact space is compact. Okay, and we will see why we will need this. Okay, so the proof is very easy. So the compact means that if you have any open cover, there's only finite subcover, always a finite subcover. So let's say you given a CA, which is open cover for A, right? So basically, CA is just some CAY create right? You have an open cover, such that O and CI union will be cover A. Then by definition, okay, so this picture is really bad. You can show that union of this CI union with Rn delete A will cover K. Maybe we see some stupid picture. Okay. So this is A, and this is K. This red is K, and the small is A, and this green is CI, right? So if you negate K, A, and see all the purple line outside A, which will indeed cover K, right? So union Rn delete A will cover K. By definition, K is compact, so there is a finite subcover such that Ni Ci union Rn delete A cover K, right? But less such Ci will cover A, so we prove, right? Any finite cover always, any open cover always a finite subcover. By introduce Rn cross A as like a mediation. Oh, I should have mediate. Sorry. Okay. Okay. So now proof is very simple, right? Since that we want to show that now is A is closed and bound, right? Since it's bounded, right? So I can find a very large ball with the cube, a very large cube with length AA to the power n, right? Basically cross n coordinates. Let's call it B, right? A will cover B. Okay, so the idea is that we need to show B is compact. Okay, right? Because A is closed. A is already closed, right? We need to prove that A is closed. We already need A. We already use A is closed and bound. We already use A is closed and bound, right? So the final thing is that we need to prove A is compact. Then A is closed subset of compact set, so A must be bound compact. So we only show is B is compact. Okay, so. I don't think we use okay, maybe we use a bijonal wire truss. Okay, nice. So B is compact, right? So we need to prove B is compact. So we need to prove that by definition, right? Things weird. So we need to prove that suppose we have a finite cover, any open cover, then we must have finite subcover. So let's assume that suppose not there exists some covering of B which no finite subcover. Okay, so that means you choose any CI. Finite, there's any finite CI cover in the union will not cover B. Okay, so the idea is that you view B as a cube in n dimension, and you bisect in each, right? So let's say the first is T1, so T1 will contains 2n per block. You usually bisect. Okay, so by definition, since there's infinite CI coverage, right? So at least one block. So there's one block that has infinite cover. Okay, the reason is that if all the blocks have finite cover, then finally the union will be finite cover, right? So at least one of the small block has infinite open cover. Infinite cover. You always need infinite cover to cover some small box, right? So you have B, and we can keep going. So we can get a B cover T1, cover T2 up to Tk, and each K must have infinite cover by definition, right? Right, but now we can pick a xi belongs to ti. So we pick a series sequence x1, x2, keep going, and by bosonal wire truss, right? This xk is a bounded sequence. So there must be a bounded subsequence. So all of these x must converge to some x naught in B, right? Why in B? Because final then in B because by bosonal wire truss, right? You're already in B. So the converge must in B because B is closed, right? We know that B is closed. So your x naught must in B. So, but B is a union. B is like union of Ci, right? or a subset of union of Ci. So there exists some C tilde such x naught belongs to C tilde, right? And remember that C tilde is open, right? So there exists a small ball which is x naught B. There's a radius of R such that the open ball of BRX naught belongs to C tilde. Not only that, right? Because TK, the length of TK goes to 0. Okay, so this is the stage that we prove up to now. Okay. So the important thing is that because TK goes to 0, right? And at least R has a finite size. So for large enough K, all the TK will fall into this BR X naught, right? Because TK cover X naught. So TK will be smaller, but there always exists finite R such that TK falls into this ball. But this ball is basically the subset of C tilde. That means for up to some K, up to large enough K, all the rest of TK can be covered by one cover, right? One cover C tilde inside C. But this contradicts our assumption. Our assumption is that each K must have infinite cover, right? But we prove that there exists some K large enough, then TK must be covered by one such C tilde. So this is contradiction. So that means the A is compact, right? Because now B is compact and A is a closed subset of compact set by a lemma which A is compact. So this proves the Heine Borel Theorem. Okay, nice. I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.